Hi everyone and welcome to JP Academia. After discussing electric field and electric potential, we will now talk about capacitance. Capacitance is defined as a measure of the ability of two conductors to store charge given a potential difference between them. Capacitors is just an electronic component used in everyday life that includes electronic filtering, remote sensing, and even in modeling how our neurons transmit signals. Let's start this lecture. This is the outline of this lecture. Now, let us consider these two conductors with charge positive Q and negative Q respectively. Note that a conductor is an equipotential, meaning the potential difference at any 2 points within or at the surface of a conductor is zero. Since the electric potential is constant in a conductor, we can express this potential difference between the two conductors. We have delta V is equal to V plus minus V minus, and this is equal to this line integral. We know from the Coulomb's law that the electric field is proportional to Q. Note that here I am expressing the charge Q as a volume charge density, or this is just the amount of charge on a given volume of the material. So we have Q over V. Since the electric field E is proportional to Q, the charge, it is also proportional to the electric potential V. And therefore, we can have this expression V is equal to 1 over C Q. The constant of proportionality is called the capacitance, this letter C, and therefore we have this expression. Capacitance is a geometrical quantity, meaning it is related to the size, shape, and separation of two conductors. It has as a unit of farad, so 1 farad is equal to 1 coulomb per volt. Note that the capacitance is usually small, and we commonly use microfarad or picofarad. I want you to remember that capacitance does not depend if they have charge, certain charge Q. Similar with a 5-liter bucket, let's say. It does not depend if it has water currently. We can find the capacitance using this general procedure. You should have first the charge, positive Q and negative Q on two conductors. Second, find the electric field between these conductors. In this step, you may use or you may apply the Gauss law. Third, find the magnitude of the potential difference between the two conductors. You may also use this line integral shown here. Fourth, given that the electric field is proportional to Q, you can find the capacitance C using this relationship. So we have your electric potential V is equal to 1 over C times Q. And your C is your capacitance. Okay, now let us find the capacitance of this parallel plate capacitor with two metal surface with area A and place at distance D apart. We place a positive Q at the top and negative Q on the bottom plate. The surface charge density, now I will define this one, is just the charge Q over an area A of the plate. The electric field between the plates now is equal to sigma over the epsilon naught. And this is just a result using the Gauss law, which shows the total flux of electric field through a surface is equal to the charge density inside that surface over the epsilon naught, as shown in this equation. Then we can get the expression for the capacitance using the following. So first, we can use the expression for the electric potential. So V is equal to this line integral. Then we can evaluate this line integral until we get this expression of our V. We can use this expression of V in our expression for V and the charge Q, wherein we have the proportionality constant 1 over C here. So this part here, this D over A epsilon naught, this refers to 1 over C. And therefore, we will have this final expression for our capacitance for the case of two large parallel plates. So we have epsilon naught A, the area of the plates, over D, their distance. Now let's talk about the combination of capacitors. For two capacitors connected in parallel to a battery with switch S, the battery gives the same voltage or potential difference across each capacitor. Also, the charge Q from the battery is distributed to the charge going to capacitor 1. So that's C1, and the charge going to the capacitor 2. So that's C2 or Q2 for the case of charge. And therefore, we can have the following derivation. So given this expression for the charge, so Q is equal to CV, we can get the total charge for C1 and C2. So we have this expression. So this is equal to C1 V1 that refers to your Q1 plus C2 V2 that refers to your Q2. But take note that the potential difference across these two capacitors is equal, and we will define it as V. So therefore, we will have this expression, and we can remove the common factor. So we have V, then we can cancel out V here, and therefore we have this expression for the equivalent capacitance for parallel. So Cp is equal to the summation of each capacitor or each capacitance value. Next, we have this two capacitors connected in series. Note that we have the same amount of charge throughout our series circuit. Thus, the charge of capacitor 1 and capacitor 2 are equal. And let's define that charge Q, just charge Q. For the potential drop, the drop between A and C, so I have this laser pointer, so between A and C is equal to the potential drop for across this one, so VAB, this one, plus VBC, the potential drop across this capacitor 2. And therefore, we can express this one as follows. So we have V1 plus V2, or this is just equal to the potential V. And we have the following. So your V is equal to Q1 over C1. So this refers to this potential drop across our capacitor C1 plus the potential drop across capacitor 2. So we have Q2 over C2 for this potential drop V2. Note that for our case, Q1 and Q2 are equal to each other, and we can define that as Q. So therefore, we have this common factor Q, and therefore, we have the following. So we have V over Q. So we just transfer this one to the left-hand side. V over Q is equal to 1 over C1 plus 1 over C2. And this is just equal to 1 over C. And therefore, we have this expression for the equivalent capacitance for the case of series or capacitors connected in series. I said earlier that capacitors can store energy. Let's talk about the energy storage in capacitors. If we have a battery connected to a parallel plate capacitor, it must do work to place charge on the plates, especially there is this repulsion due to the charge present already in the plates. Given a small charge dq and a potential difference v, we can define this work done, and we have this one. So dw is equal to v dq, and we can derive the work w by getting the integral of this. So from 0 to q, the final charge q v dq. So after evaluating this one, we will get this expression for the work. So we have 1/2 q squared over c. You can also have the following expression for the stored energy using the relationship q is equal to cv. Then we have these three expressions of your stored energy. Earlier, we defined these capacitors in vacuum, meaning we don't have any material between these two charge plates. In reality, we place insulator between the space of capacitor plates which is called dielectric. The electric field between the plates polarizes the dielectric, so this is our dielectric substance, and it induces dipole moment. It usually has polar molecules with dipole moment, and the electric field align them in parallel. So the polarization, so this is the induced charge at the surface of the dielectric. And the effect of this is the potential difference between the two plates reduce, or it also reduces the field, the external field in this system. And with that, given the same amount of charge Q, and given that we decrease or we reduce V, and therefore we increase the capacitor C. We have this property, the property of the dielectric material, and this is defined by a certain factor kappa, this one, called the dielectric constant. If C naught here is the capacitance of empty capacitor, the capacitance with dielectric C is expressed as follows. So we have C is equal to kappa times C naught. And that's it for this lecture. In summary, capacitance is defined as a measure of the ability of two conductors to store charge given a certain potential difference. Effective capacitance for capacitors connected in series and parallel were discussed also. Capacitors can store energy. Last, we have discussed dielectrics that increase the capacitance value of your capacitors. Hi, if you have learned something in this video and you like my content, please consider subscribing my YouTube channel, GP Academia. See you in the next video.